Minimum phase systems are those systems whose transfer function has all of its poles and zeros on the left hand side of the S-plane. Otherwise, if any of the poles or zeros are on imaginary axis or right hand side of S-plane, then they will be referred as non-minimum phase systems. This right hand side and left hand side is defined with respect to y-axis. If you have to find whether the provided system is a minimum phase system or not, then you have to find all the zeros and poles of the transfer function of the system and conclude the system to be minimum phase system if all the poles and zeros lie on the left hand side of the y-axis. Otherwise, it will be a non-minimum phase system. Minimum phase systems are highly recommended in designing control systems because of their particular advantages, like minimum phase systems along with their inverse are causal and stable. Also, the phase lag present in minimum phase system are comparatively smaller, and the question can be framed in which you have to determine whether the transfer function represents minimum phase system or not. Then probably there might be a case where it is easier to find whether the system is causal or not. Depending upon the situation, you have to use different points to solve the question. Now, we have three new terms which are inverse, causal and stable. Here, we will be having a general definition of these terms only, as you are supposed to study these topics in great depth in signals and systems. Stable systems are those systems whose output remains bounded for a bounded input. In other words, if we load a stable system with limited input, it will produce a limited output only. Its behavior will not become excessively erratic or unpredictable. Causal system is a system whose output at any time depends only on the present and past inputs and not on future inputs. The third term is inverse. The inverse system can simply be defined as the system which undoes the operation of the original system. In other words, the inverse system reverses the input-output relationship defined by the original system's transfer function. Suppose that we have one system whose transfer function is Hs, which is cascaded with its inverse system. Then the output in this case will be equal to input only. Both the systems having transfer function of Hs and H inverse S are inverse of each other. The overall system's transfer function will then becomes multiplication of Hs and H inverse S, which will eventually give us 1. If suppose the value of transfer function at some random value of S is provided in the form of amplitude and phase difference, where 5 is the amplitude and 45 degree is the phase difference of the transfer function at S equal to S1, then the inverse system will have amplitude of 0.2 and the phase difference will be equal to minus 45 degree when the value of S is equal to S1. And the very important point is, we deal with systems whose inputs can be either increasing type or can be decreasing time functions with time. But there is another very important category of signals which we analyze, which are referred as sinusoidal signals. The point which you have to particularly keep in mind is that when we have sinusoidal inputs, we neglect the damping factor in the substitution of complex variable s, which gives us s is equal to j omega. When the input to a system is a pure sinusoid, then there is no exponential growth or decay in its steady state. The only thing which are present are oscillations, and hence the damping factor becomes equal to 0, giving us the value of s to be equal to j omega only. There is one more way to remember this point. We use s is equal to j omega for sinusoidal input because sinusoids correspond to purely imaginary poles in the Laplace domain. There is no exponential growth or decay. Therefore, we have to evaluate the transfer function by putting s is equal to j omega, which gives us the steady state response of sinusoidal inputs. The response which we get by placing s equal to j omega are referred as frequency response. This is a broad topic in itself, consisting of Nyquist plot, Bode plot, etc., which we will cover in the later part of this series. In frequency response, we mostly ignore the damping factor. Now, try to solve a question in 4 minutes. This is a very unique question, neither easy nor difficult, but a unique question. First, we will find the phase difference between the input and output, which we will get to be equal to 30 degree. The transfer function is already provided in the question. We have simply replaced s with j omega. As I just told you that for sinusoidal inputs, we neglect the damping factor. That's why we have placed only j omega in place of Laplace variable s. The phase difference which will occur due to this transfer function will be equal to 90 degree minus tan inverse omega divided by p. Now we have 2 points. Obviously, the phase difference which is caused by the transfer function will be equal to the phase difference between input and output, and also we can find the angular frequency which is provided in the question to be equal to 2. Now we have to simply equate the phase difference from these two equations to find the value of p, which will be equal to 2 divided by root 3. I hope you have understood this question.